Okay, so welcome to our discussion for today about basic fundamentals and basic fundamentals in terms of modeling of power systems. So our topic for tonight or today is in terms of per unit analysis. So in this case, no, in this discussion, we will discuss how you will model a certain power system that is composed of transformers, connection of transformers, and we can model a power system to single phase or three phase system. So my name is Michael Pasis again, and I am from Mapua University, and this is where my information. Okay, so let us move forward to per unit power system representations. So we have here the description and the symbols of every equipment that you can see on a single line diagram. Simply because before you go to per unit modeling, you need to have a single line diagram, which we will discuss in the next few slides. Okay, so we have the following descriptions and symbols. Okay, the first symbol here is a circle. So when you have a circle, we have two types of machines that we can have the symbol. We can have a generator and we can have a motor. So rotating machine is modeled by using a circle, okay, with a G or M. We have a two-winding transformer. So a two-winding transformer, we have a coil, a single phase, two-wire system. However, if we have uh, connections like this, Y to delta, delta to Y ground, Y ground, you're considering the system as three-phase, three-wire system. So it means we can simplify things instead of having three coils connected between lines. Okay. Next is a fuse. So a fuse is a protective device that is can be which is automatically uh, if there's a fault, it will automatically open. Okay. So this type of protective devices is in terms of per phase basis. They are connected in a per phase basis. Okay, this for protection purpose. Now you have also a current transformer. Okay, a current transformer is like this, connected in series instead of shunt. Okay, and we have a potential transformer in the next slide like this. A simple coil connected in shunt, and this is a potential transformer. Okay, both of these transformers, current transformer and for potential transformers, are for experimental purpose only. Okay. Now I can clear all of the drawings so that we can go to the next slide. Okay, the next slide here pertains to the other types of symbols and the corresponding description. Okay, we have already discussed a potential transformer, and then we have the oil circuit breaker. Okay, the oil circuit breaker is a type of breaker that uses oil as its corresponding insulator. Okay, it has some properties or characteristics. Also, another type of type of breaker is an ACB. So ACB, it means an air circuit breaker. Okay, it's like a hump. Okay, in a road. Okay, so it is an air circuit breaker. Okay, we have some of the connections here. It's very obvious that you already know this one. You have a delta connection, a Y connection neutral grounded, a Y connection ungrounded bus bar. Okay, a bus bar can be also represented by a node. Sometimes single line diagrams is represented instead of a bus bar you have a node. Okay. Also, there are some symbols here which is not represented on this slide. So, like loads. Loads are represented by open symbols, on open-ended symbol like this. So it means that is a load. Also, it can be represented by a ground like this. Okay. This ground, this is different from the load. Okay. So you load, you have a ground like this. So again, we need these symbols here, and if we interconnect all of them, create a single line diagram, which is a very, very, very vital diagram for a power system engineer or an operation engineer. Okay, so that they can see the operations, they can analyze the steady state performance. So it's very obvious that it's a very important aspect to know the types of symbols, and then when you integrate it, you can have a single line diagram. Okay, let us clear all of the drawings and let us move forward to this slide. No? Okay, this slide here is a one line, the description of what is a one line diagram all about. It provides a compact way to represent a great deal of information of every component, which is you need the ratings of a machine, a transformer, the power consumed, and among others. And then the impedance of the lines and devices are already incorporated in the system, and that is a single line diagram. So this is an example of a one line diagram wherein you have a generator, okay, a transformer. Okay, you have a generator, you have a transformer, and you have a group of loads, no, which is your motor loads. And it is protected, okay, by an oil circuit breaker. So these are protective equipment. And again, if you have a, the every description of every symbol, you already have an idea what are those. Now, this more complex if you're talking about a generator or substation design, simply because complex system diagrams are incorporated there. For example, you have types of relay, and overcurrent relay is also different from a frequency relay, is also different from a power relay. It needs the device numbers, etc. So the fuses are different, the isolator switches. So in our in modeling of a certain equipment, or rather certain power system, we will just draw the power system in a much simpler way. So sometimes we eliminate the protective devices. We just draw it in a line instead of having all of the protective devices incorporated on the power system. So that's it. Now, one more thing is, please take note, no, of this. No, when you have a one-line diagram, other name for a one-line diagram is an SLD. SLD means a single line diagram. Please take note of the following. Okay, a single line diagram is a per phase representation of your power system. Which means when you say a per phase representation, you're considering the power system as balanced. So if the power system is balanced, you can use the PPA or per phase analysis in order to analyze a certain system. If you can still recall your polyphase, balanced polyphase, right? You have a three-phase power system, three-phase generator, and a three-phase load, and three-phase lines. If that is balanced, you can use one phase of the system. Particularly, the reference is phase A. So we will make use of this. Okay, phase A. Particularly, the phase A is our reference because if you compute for the power, or you compute for a certain parameter, for example, power, just multiply by 3 because the other phases is the same with phase A, right? You have only 3 phases. Okay, so please take note of that. The when you say a one-line diagram is a per phase representation of a power system. Okay, we can clear all the drawings and we can go to the per unit systems. Okay, here is the next slide here. Okay, so now we know what is a power system, what is single line diagram all about. The question is, how can you analyze a certain system? You need to have the fundamental of a per unit system. Okay, if we go back to this last slide, no, if I ask you, no, to solve for the motor current, I could say IM. How can you solve a certain parameter if there is a transformer here? Okay, so you need to eliminate the transformer, not typically eliminate the transformer, but you need to model the transformer in such a way that this will become a per unit equivalent circuit. So if your transformer is modeled as a reactor, then you can have a per phase representation of the system in terms of AC circuit. Okay, so it means, okay, that per unit analysis is can model a single line diagram to its corresponding AC circuit or per unit equivalent circuit. PUEC means per unit equivalent circuit, which is an AC circuit equivalent. Okay. So it provides a compact way to model a power system composed of many transformers. And from there, you can analyze the operation of a system, or computing the variables that you need, in the system or the power system itself. You can clear all the drawings, and that is per unit systems. Okay, now the question is, what is the formula for per unit systems? So the per unit is just as simple as it. Whatever the actual value, you divide it with the base value is per unit. Okay, so the question is, what is the unit or per unit of a per unit system? Obviously, dimensionless, because if your unit on your actual, which is this actual value, are the given values on your power system. You have the voltage, you have current, you have the impedance ohm. Then it can also be the base quantity value is the same unit, so it will cancel parameters. And thus, if you cancel parameters here, you're considering the system is dimensionless. It's dimensionless. So no unit. Okay. Okay. Now let's continue our discussion, especially to the formulas. The formulas here is like Ohm's law, right? So these are the typical single phase system relationships. And considering again this scenario, okay, we model the power system, especially the transformers, as an ideal transformer. So what is ideal transformer? A transformer that is lossless. A transformer that the efficiency is 100%. And the angles are unaffected on both primary and secondary sides. So that's why the power basis and the Q basis and S base is simply equal to V base times I base. So there's no cosine or sine angle, simply because we are considering all of the transformers along the power system ideal as possible. And one more thing, when you say an ideal transformer, whatever the input power at the primary side will be the same at the output power at the secondary side. And the rest is simple Ohm's law. Okay, computing Z, computing Y, and this equation here, which in terms of voltage, V squared all over S base. Okay, let us clear all of the drawings and then move forward. Now, in terms of three-phase systems, okay, the only difference is the voltages, okay, is in terms of line to line, and the total apparent power now in terms of ST. Please take note, okay, that we discussed from the previous slide that the line to line voltage is simply square root of V phase. In terms of three-phase systems, the total apparent power is 3 times the power per phase. So what you will do is just organize this equation like this and then substitute these parameters in these equations. Okay? And then it will yield an answer that some of the equations will be divided by square root of 3. Okay? So you can see the formulas here, just substitute in terms of line-to-line values and total apparent power ST. So, if you do so, okay, we can have these equations at the next slide, which is a very, very important equation for three. Okay, please take note of the following before you compute for three-phase systems. Okay, first you need to check if all of the apparent power or the powers on the system. This is only for three-phase systems because in terms of single-phase two-wire, it is unaffected because whatever the power is just S. There's no multiply. However, if you have a three-phase system, you need to see if the apparent power are total, all of the voltages are in terms of line-to-line basis, and last but not the least, the impedance are in terms of Z per phase. So what's the meaning of this? It means if you have a Z per phase, you consider all of the loads connected in Y. Because the only way to have a per phase analysis is you need to have a Y connected load. If that is the case, you have a Z delta, you want to convert it to Y, you need to divide it, the Z delta by 3. Okay? And you can use the following, and the only difference from last single phase per unit formula is the square root of 3 at the denominator side. Okay? Okay, next. Another important formula that you need to know for per unit analysis is the so-called change of base formula. Okay, the change of base formula has this representation. Per unit Z nu is equal to Z per unit Z given, V given over V nu squared times S nu all over S given. Now, we can have these synonyms, by the way, so that you will not be confused on some of the formulas later. You can use the base here. The base is also the same with nu. The given is the same with old and the same way with rated. So these are synonyms. So it means they have the same definition. Okay? So you will use this formula if you see percentage values of the impedances. For example, you have a transformer and there's a percentage impedance here, I could say 5%. Okay, you need to convert this parameter, this given parameter, to its corresponding basis, which is dependent on the base computations of the system. We will make use of that later. So what's the moral lesson of the story here? You will use this formula if you see percentage values along the power system or along the um, uh, rotating machines or equipment, transformers, and motors. Those are typical equipments that you can see percentage reactances. Okay. Sometimes not percentage reactance, but percentage impedances, which is composed of R and X, or real and imaginary parts, respectively. If we go back to our slide, okay, here, this formula, where you will use this formula, when you will use this formula, you will use this formula if the given on a certain equipment is actual values. If the given is actual values, then just divide it by the base value, you can get the per unit quantity. Okay. Not unlike the second equation that I gave, no change of base. If the given is in terms of percent, then you need to use this formula here, which is the change of base formula. By the way, there's an equation here, which is R base, Z base, and X base. Why they are equal as well? Because you're considering a ideal transformer. Because they have the same angle in terms of the power formula, right? So it means the two angles here, which is represented by this drawing, are the same. And thus, considering in terms of Z, R, and X, they are the same also with S, P, and Q in terms of the ideal transformer. Okay. Okay, now before we go to the calculations, we need to have the following conditions in the system. So first, S base and V base are pre-selected or selected at a specific point in the power system. And one more thing, no, when you say an ideal transformer, the output powers is equal to the input power. Okay? Whatever happens, input power is always equal to the output power because we use an ideal transformer. And thus, okay, in a single phase system, also in a three-phase system, the S base will always be constant all throughout. The power will be constant all throughout the system. Okay? But the voltage base will change when it goes in or out of the transformer. Simply because what will be the function of a transformer if it does not convert voltage or step up, step down voltage or step up, step down current, right? The only thing that is, when we say ideal, is the power and the angle. They are unaffected in the input and output sides of an ideal transformer. So, S base is constant, please remember that, while V base will change in a transformer. Okay, so I think let's go or move forward, move to the next slide since this just a the discussion or recollection of what you already know on your undergrad. So, what is the power conditions, no, for single phase and three phase systems? So it simply means, okay, that whatever happens in a single phase and three phase, the treatment is like a per phase basis. There's multiplier by three. So the technique here, if you have if you have a three phase system, please take note of the following that I've discussed on the last slides. If that is three phase system, the power is ST. The voltage is line to line, and the impedance is per phase basis. But if that is a single phase system, you do not need to know that simply because in a single phase system, ST is S phase and VL and is simply equal to line to neutral. So you do not need to check those parameters. Okay. So that's the meaning of this slide, that the powers on a single phase or three phase units are unaffected simply because if you have phase, the three will cancel out. So the treatment is per phase basis on a apparent power total ST. Okay, and the rest are important things. Okay, so for example, in terms of in per unit, the system must be balanced, as we have mentioned on the previous slides. So again, this is the rather this is the proof here in terms of line-to-line voltages. Also, you do not need to divide no or divide it by three, no, the impedance as long as it in terms of per phase basis. The line currents are the same. You do not need to multiply it by 3, the total power. And one more thing, if the system is already modeled in per unit, you consider the phase angles of the voltage must be zero for reference. By the way, and please take note as well, okay, that if you have a three-phase system and there's an angle in terms of the voltages, please take note that the VAB, no, will be our reference, or the voltage at line A is our reference in terms of three-phase. There's an angle, but if there's no angle, for example, you have a generator and this is 13.8 kilovolt, it means this is automatically VAB. This is three-phase systems, huh? You're considering three-phase, three-wire system. VAB is 13.8, okay, kilovolt bar zero, unless stated on the problem. Okay, now I think it must be uh, much clearer if we have a sample problem or an example. Okay, so let us solve this problem here. No, so you have a 50 MVA, no, 34.5 by 161 kilovolt transformer having a 10% reactance is connected to a power system where all the impedances values are on that base 100 MVA 34.5 or 161 kilovolt. The question is, what will be the new reactance of the transformer with respect to the new base? Okay, now we can solve this problem with ease simply because you already know the new value or the base value as we have discussed on the synonym words. So you need to convert the percent reactance, okay? So when you will use the change of base formula, if there is a percentage reactance given. So this is the right opportunity for you to apply that formula, okay? Now you have the given value of the 50 MVA 34.5 161 kilovolt transformer. You need to convert the 10% reactance to its new base by having the new bases on the system, which is the 100 MVA. This is an S base on the system. Typically, the S base of the system is any number that you want. Okay, so even your last two numbers of your birthday, even your favorite number. Okay, but no, since we are in theoretical and sometimes we need to be consistent, we usually use a 100 MVA as your S base. Okay, so you can choose any value that you want. The answer is still the same. But again, if there's no given the problem, you can assume a 100 MVA base. Okay, applying the formula that we have on the change of base, which is this, then you can already substitute no the parameters in the system. Now I have we check here no on the solution that we can refer to the primary and we can refer as well at the secondary. The answer is still the same. Okay, simply because as you can see, if we have this on two lines, okay, the 34.5 is primary, secondary, 34.5 primary, secondary. If you substitute all the parameters in this formula, okay, considering whatever the primary or secondary reference is, if you refer it primary second, on the theory of transformers, they are the same. Whatever the reference that you have, no, primary man or secondary. Okay. So this is a very simple problem which um, use the change of base formula. Okay, let us move forward to another example. Okay, where in this example is a transformer example as well in single phase. And then we can use the primary or secondary basis of the transformer. Okay, but this is a different thing because instead of percentage, the given is in terms of actual. And in this example as well, you can appreciate that it's much better to use the formula in terms of whatever the reference is. You can refer to the primary or you can refer to the secondary side. And please take note, since the given is in terms of ohms, you need to have the formula of per unit is actual all over the base as our solution here. Okay, let us read the problem first. You have a single phase transformer rated 20 kVA for 120 volt, 60 source. The equivalent leakage impedance of the transformer referred to the 120 volt winding denoted as winding 2 is ZEQ is equal to 0.0525 CIS 8.30. Using the transformer ratings as the base values, we need to determine the per unit leakage impedance referred to winding 1 or winding 2. Okay, before we proceed with anything else, you have a CIS here. So what's the meaning of that? The CIS means no cosine imaginary sine. So it means, in other words, this is the bar angle. Okay? So by further of the impedance, no? That's the bar angle of polar representation. It means this is the bar angle. Now, let us have the solution here. We can use the 120 volt base first, secondary side of the transformer first. So it is much better in this way. This is the will give us the answer right away. Okay. Again, from the first example, we can have primary and secondary. Now, and please take note, you have two bases here, and the S base here is constant all throughout. Please take note, there's no uh, underscore, there's no number, there's no subscript on the S base, meaning to say that is constant. Okay? So, applying this formula here, B squared all over S, we can have 0.72. Now, you already have the Z base. Just divide the actual value by the base directly. But again, it must be at the same winding. The answer is simply 0.0729 bar 78.13. Okay, how about if I apply it on the primary side? Is they will have the same answer? Yes, you anticipate that you will have the same answer. Okay? Perhaps you can practice that one, no, if you want. But again, we have the solution here. Now you can have the opportunity now to get Z base 1 by having B base 1 squared all over S base. Please take note, there's no subscript simply because that is an auto transformer rather than an ideal transformer. So you have a 11.52. Dividing 0.84 by 11.52 by per unit is equal to actual all over. Then it will yield with the same result. So the moral lesson of the story is, whatever your reference is, it can be primary or secondary, you will anticipate the same answer. So when you compute for a real power system, you can have left or right, or primary, always primary, or secondary, secondary. It's a choice. Okay, but again, the answer is still the same, simply because in a per unit system, they use a ideal transformer. Okay, now a much better way to understand this one is a single line diagram here, no? So we have an actual power system now, and then what you will do first is to solve the problem here in terms of per unit equivalent. So it means you need to convert it to per unit first. You need to regionalize the power system. So what we have already described on the few topics or the topics on your power system protection, that you need to regionalize the system in order to have area number. So in this case, you can regionalize the power system depends on the substation or the voltage of the substation. And please take note, in regionalizing a system, it must be the same voltage per region. Okay, let us solve. Let us read the problem first. No, on this final example, for a three-phase power system shown below, and showing all of the differences in per unit on a 100 MVA base. As I have mentioned, you can use any MVA base that you want, but if there's no MVA, you can assume an 100 MVA base. There's an inductive load, no, 48 megawatts connected, no, with a power factor of 0.6. So you choose a 20 kV as the value of the voltage generators and assume all voltages as a line-to-line rating. If the voltage at generator 2 is limited to 18 kilovolt only by a substation at bus bar 2, which is your transformer, we need to determine the per unit circuit, and last but not the least, you need to get the load current. Okay, this is what I meant, no, on our introductory. Okay, you cannot solve the load current here if we do not model the generators in its corresponding per unit reactance or impedance. It depends on the given. So you can see here, it will become impedance because you have an R and X given. Okay. One more thing, as I mentioned, before you start any solution, you need to check if all of the parameters of the powers is total apparent power. Now, it is not mentioned on the problem, the 90, 80. Okay, this one, 80 again, 90. There's no phrase or statement in the problem if that is interface basis, but you can treat those powers as total, and it's also given that all of the voltage here must be in a line-to-line basis. That is checked. And last but not the least, no, the impedances, if there's any, is on per phase basis. So again, it is satisfied. You can see at the load side, instead of impedance, it is given by S. So we can already compute, no, for the system here, for the requirement of the system in terms of per unit, simply because we satisfy all the three things. And last but not the least, you need to know where you will start the solution. You will start the solution in terms of wherever the voltage is, the first voltage that you want, of what region. Because you can solve the problem in region 1, region 2, region 3. But typically, okay, so that you will not have a hard time, you can assume that the ratings is, or the base ratings is on the source. Okay, so we start at the source, which is, it's also given on the problem that we will start at the source at 20 kV. Okay, so you can still understand this fully on the solutions on the next few slides. So we can clear this out and then go to the solution proper. Okay, the solution proper is straightforward. Okay, so first, you need to have the base computations. And please take note, by the way, okay, by the way, before we go forward, that before you model a per unit equivalent circuit or PUEC, before you do this, okay, please take note on the modeling itself, no, on the base computation. You need to get first V base and Z base. Because in a system, on a circuit, you usually see voltages and impedance. But current, you care. Even on calculations, we calculate them. So it means all the passive components and the active components is only present at a per unit equivalent circuit. So to conserve time, okay, we can have the base computations in terms of V base and Z base respectively. So if you do so, choosing V base as 20 kV and an MVA as 100, so we can get the impedance directly. By the way, there's a shortcut, by the way, in getting Z base. As long as the voltage is in kilovolts and the MVA is in terms of or the S is in terms of MVA, you can use the KB squared all over BA formula here. Okay, thus, this is what happens here. You have 20 squared all over 100, and the answer is 4. Okay? And using the transformation ratios, right? Which is A is equal to V1 over V2. This can be also applied in terms of base computations. So you can get the base voltage at the second region by dividing V base 1 by A1. And what is A1? The transformation ratio, right? It can be number of turns, it can be voltage, it can be impedance, or it can be an N, or number of turns, or impedance and current, right? Okay, if you do so, well, we can compute for the basis of the system a straightforward solution and the Z base as well. So please take note, the only parameter that does not have a subscript is your S base or MVA base. Then do this on the other regions. So it is already self-explanatory that you can do this already by analyzing the circuit above. Okay. So the parameters that is important here is V base, Z base, and on the other regions, V and Z. Now, how about the current, sir? Where I will compute that. You will compute that if that is necessary already. It means you want to get the current, the power factor, the losses. Now, you need to have the current basis. Depends on the computation of your V and Z. Simply because you can get I by having V all over square root of 3Z because this is already a three-phase system, right? Okay, now, after you compute for the base computations, okay, we can now go forward, okay, to the conversion of the per unit impedances of the power system using this formula. So we have already proved that we can use the primary of the system voltage or the secondary. I use here the primary. I refer this one in the primary side of the transformer. So in this case, we can already have this values in terms of per unit using the ratio base formula. Okay, please take note that the constant parameter all throughout is the 100 MVA because it will not change. And the squared here is the voltages V given over V base. Okay, and thus, using the principle that we have from the last slide, we can now get the impedances XT1, XT2, XG1, and XG2. And remember, we make use of the change of base formula if the given on the problem is in percent. As you can see here, what I'm talking about is these values here. Okay. So those values there are in percent. So you must model the system in per unit using the change of base formula. Okay. Let us move forward to the other parameters. Okay, we can get the active and passive elements of the system, and we use the formula of actual all over the base because we need to model the parameters in per unit if the given is in volts, in ohms, okay, respectively. Okay, now you can see here the value of the voltages here, which is 20 all over 20, which is actual all over the base. The kilovolt is cancelled, okay? Because at G1, the base voltage at region number 1. At G2, the voltage is at region number 3. You can recall the power system. So just get the ratio, actual all over the base, you will have the per unit values of those parameters. Okay, and then you can now model the passive elements. So again, what is active and passive element? Active sources. Passive, it means loads and transmission lines. Any equipment that is absorbing electrical energy. Okay, now, as you can see here, this is your load magnitude, ZMAG. Okay. We have that one in terms of the given here. Okay, so you have the parameter here. Okay, 200, no, all over 80. Okay, so 200 kilovolt, you divide it by 80 here. Okay, so the 80 here is your S. Okay, go back here. Okay, if we go back to the triangle, and you have the angle here, you must get the Z magnitude using the formula of V squared magnitude. You divide it by S magnitude. But the given here is in terms of 48 megawatt. So in terms of P. And the power factor is 0.8 log. So if you have your triangle SP and Q respectively, okay, you can get the power factor here, which is simply equal to your P, you divide it by S. Okay, you can get S here by dividing 48 by 0.6. Definitely the answer is 80, by the way. Okay, the answer is 80. Yes. 80 megawatt to be exact. And use KB squared all over MBA. And that's why you say KB squared over MBA. That's why the answer on that slide is 200 squared divide by 80. Okay. So we can clear the drawing again and go back here. Yes, we have that magnitude. However, to get Z per unit here, to model the Z per unit, it must be in vector. So it must have the Z actual vector. You divide it by Z base. Please take note, by the way, before we go forward. This is just a review. When you have a base complete, the value must be in terms of magnitude. All of the parameters that you compute, no, on base computations are what? Magnitude wise. So it means when you divide it, there's no angle. Okay? So in our example here, you already have the magnitude of 500. The answer is 500 on that ZM. Okay. But you need to have phasor. It must be Z bar angle theta. And the bar angle theta is depends on the power factor, right? And you have 0.6. So get cosine, the inverse of that cosine, you can get the angle. So the angle of 0.6 is what? 53.13. Since that is lagging, lagging means a positive angle. Okay, and you divide it by whatever the value of your Z base at the second region, because the load is connected to the second region, you divide it by 400. And the answer is already here. Okay, 0.75 plus J1. And last but not the least, you can design the transmission line impedance, no, by having 120 all over 400. And the answer is J.3. So all of the highlighted parameters that you are seeing on the slides is simply your parameters of your per unit equivalent circuit. And thus, we can conclude already, okay, all of the parameters that already computed on the last few slides, and we interconnect them as we have expected, you will have this per unit equivalent circuit. And thus, as I mentioned, this is an AC circuit. Okay? So, use your AC circuit fundamentals in order to get the current there. There are many ways. You can use nodal here, of course. You can also use Millman's, or you can also use mesh forever or mesh analysis. So there are many techniques, and that is dependent on your technicality or your analysis on circuits. Okay. And thus, if you do so, the answer for the load current there, no, in per unit is 0.6756 bar 123.5, and we have the opportunity now to get the base current, which is the second region. And you can use no the formula V base 2 all over square root of 3 of Z base 2. Please note that the 1.732 here is equivalent to square root of 3. And that's the answer in numerical value or magnitude. The answer is 195.03. So that concludes our discussion on basic fundamentals. So see you on the other videos, especially in terms of short circuit and load flow.